Welcome back. We're continuing our discussion regarding percent yield, which you may remember is actual yield divided by theoretical yield times 100%. We talked about your mark in a math test. If you have 16 out of 20, the 16 being the actual yield, the 20 being the theoretical yield, and of course your percent yield would be 80. Not too bad. Now, let's take a look at a question in actually the PowerPoints that I've given you. We're going to solve this top to bottom, and it does go through a lot of concepts that we've been talking about in the last few videos. And this reaction involves putting together phosphorus, which is a solid, very dangerous reactant, by the way, reacting with chlorine gas. Not a reaction that I would have you do in the lab because it's very, very explosive. The product of this reaction is PClO3, which is phosphorus trichloride. The balanced equation is given, and you can see that our equation line is written down below, very methodically. Let's suppose in this reaction, we're giving you 12 grams of pure phosphorus, and we're giving you 35 grams of chlorine gas. The question is twofold. Number one, what is the limiting reactant? And number two, what would be our percent yield if you were to step into the lab and actually get 42.5 grams of product produced? That's the question. Well, let's take a look at it and solve. Just like before, our first step, whenever we have masses on the reactant side, is to convert both of those values to moles. So we can easily do that using our periodic table and our calculator, which you should always have out, and we get 0.387 moles of phosphorus, and we get 0.493 moles of chlorine. Because the ratio of phosphorus to chlorine is 2 to 3, and this number is a little smaller than that one, it's probably too close to tell which reactant will indeed run out first. So we do the handy-dandy check that I've explained to you a few times. Always involves the experimental data divided by the equation data, and then we compare ratios. So after all said and done, if we take our 0.387 divided by 2 for phosphorus, we get 0.194, and likewise if we take the 0.493 divided by the 3 moles of chlorine, we get a little bit less at 0.6164 for the chlorine. What does that tell us? Well, lo and behold, it tells us that the chlorine is a limiting reactant. When it runs out, the reaction's over. And we now know that the phosphorus is no longer important, and we're going to put an X through that number of moles because there's more than enough to go around. This is a number important to us, the 0.493. Now, we have to find our theoretical yield of our product because this was the actual yield that somebody did in the lab. And we're going to use it later. So, when we look at our mole ratio, we need 3 moles of chlorine for every 2 moles of product. So it stands to reason that when we take this number, we multiply it by what we need over what we have, which is 2 over 3, and we get 0.329 moles of PCl3. We're working toward our theoretical yield in this case. The last step in this process is to convert our moles to grams. Grams equals moles times molar mass. The 0.329 times the molar mass of PClO3 gives us 45.2 grams, which is our theoretical yield. Remember, this is what you should get if you did the experiment perfectly. But we're all humans, we're not perfect. This is never going to happen. So when you did the experiment, if you can imagine that you did, maybe you only got 42.5 grams. Not too bad, but not perfect. The question is, how well did you do in the lab? We know that we can find easily how well we did. The percent yield, remember, is equal to the actual yield divided by theoretical yield times 100%. That's from the last video. That's in section 7.5. We can plug this data in quite simply because our actual yield is 42.5 grams and our theoretical yield that we just calculated is 45.2. Pretty good, but not perfect. And after all is said and done, when you do that math, we come up with a number of 94%. Again, a very good yield for a grade 11 student. Really a good yield for any student, for all that matters. And that's the end of the story. Number one, we have to find our limiting reactant. We can ignore the reactant that's in excess, just like we have all along. Use the limiting reactant to find the mole ratio of products. In this case, we're only going to get 2/3 as many moles of product back that we started with. Find your theoretical yield, your perfect yield in a perfect world, and then plug it in to this simple equation to find the percent yield. Hopefully this helped. This pretty well takes us to the end of the material in Chapter 7. Very exciting. Hopefully this helped and you can try some more problems in your book and the problem set should become easier for you.